Okay, so today we're going to specifically look at polyprotic acids. What do you know about polyprotic acids and how they dissociate? What have we learned so far? One at a time. They dissociate stepwise. So that's what this little bit here shows you. And then you can also see that it says one important point is that after a proton is lost, the next proton is lost less easily. This means that the acid becomes weaker and weaker and weaker. So one thing that you guys will need, so kind of mull around and find it in your notes, you need to have that table of acid, K's of acid table ready to roll. And if you notice, if you look, there is a section specified for polyprotic acids. And if you see, what is it called? Yeah, common polyprotic acids. And if you notice, there's multiple Ks. So depending upon how many numbers of steps it takes to dissociate, that's going to tell you how many Ks you have. What can you notice about the Ks as you go from Ka1 to 2 to 3? They get smaller and smaller. That's because it gets harder and harder for the proton to dissociate each time. Okay? So I need to change this ink because this ink is so depressing. What color do we want today? Pink? All right, we'll do pink. Let me go find it. Like this pink? Licorice? That's kind of what I'm already doing. Is licorice, oh, you mean red licorice, or do you mean? Oh, I didn't see it. It was probably just black. All right. So the whole assertion where I say the first proton is the only proton that matters and we never look at the second proton when we're trying to find pH, I'm going to prove it to you. You're never going to have to do this on your own. Teachers, some think that I'm crazy for doing this, but I want you to see why. Why does the second one not matter? And so, rather than just telling you. So for practice, let's go ahead and write the two dissociation equations associated with that carbonic acid dissociating. So we're going to start, and we're going to dissociate this into what? Stepwise. No, stepwise. 8CO3. Gosh, look at what is wrong with me? No, I want you to go away. Cut. HCO3 minus plus H plus, right? Okay, so now let's dissociate the second step. And we get CO3 minus 2 plus H plus. If the initial concentration of the carbonic acid is H2CO3, is 0.1, calculate the H plus. In your calculations, assume only the first dissociation occurs. Note the equilibrium constant for the first dissociation, Ka1, is 4.3 times 10 to the negative 7th. All right, so what we're going to do is do a Rice table for just the first step. We can do this pretty quick because, again, this is me trying to make a point, not something you're going to ever really have to do. So we have our dissociation. Our initial concentration is 0.100, 0, 0, minus X plus X plus X. So we get 0.1 minus X, X, and X. We can trump this. So our Ka, and this time since it's the first step, we're going to go further and say Ka1 is equal to the H plus times the HCO3. And if you guys are ahead of me, go ahead and do the calc, divided by the concentration of H2CO3. So I'm going to plug in my Ka1 of 4.3 times 10 to the negative 7th equal to X squared over 0.1. So the question is asking for the concentration of H plus, which is equal to what? X. So X is equal to H plus, which is what value? Can I get a second on that? All right. Just for grins, take the negative log of that answer and tell me what the pH is, even though it didn't ask for it. 3.68. So everybody agrees with this number. They got something different last period. Shocking. All right. I don't know. I don't remember. I don't memorize these numbers. Well, if all of you are saying it, I tend to believe you guys, because I'm lucky if I can get one person to speak. Anyway, so this is potentially our H plus concentration in moles per liter. Now, the second step, we understand if we make more H's now, we're contributing to this amount. So any additional H's we make, we're going to have to add to this. So the cool thing about this is we're going to do, and I'm going to do the next question I have on the next slide, but I'm just going to do it right here. So the next question is saying, now consider the second dissociation equation. What is the initial concentration of the HCO3 and the H plus? When we do our second dissociation, it is super cool because what are our initial concentrations of HCO3 and H plus? Don't we start out with what we ended up with, right? So whatever we got for X is going to be the initial concentrations for the next step. So our next step is HCO3 minus goes to H plus CO3 minus 2. The initial concentration of HCO3 minus is what? 2.07 E negative 4. Our H plus, it also has an initial concentration of 2.07 E negative 4 and 0. So our change, minus X plus X plus X. So we get 2.07 times 10 to the negative 4 minus X. 2.07 times 10 to the negative 4 plus X and X. We're going to trump this just for the purpose of solving X. I'm going to trump this X and this X. So when I do my K, what's Ka2's value? I can't see it on this page. 5.6 times 10 to the negative 11th. The Ka2 value is 5.6 times 10 to the negative 11th. And I'm going to set that equal to basically X times 2e negative 4 divided by 2e negative 4. See what I did? I just dropped the x's. So X is equal to 5.6 times 10 to the negative 11th. And if I want to know the true concentration then of H plus, what would I do? Add it to what we had there before, right? So give that a whirl in your calculator. 2.7 times 10 to the negative 4th plus 5.6 times 10 to the negative 11th. Tell me what you get. .07 times 10 to the negative 4th. Nothing changes. This number is so small mathematically, it's going past any sort of accuracy we can handle in the lab, right? So this ends up being the exact same number. So when I say mathematically negligible, that second step is not changing that concentration, which is not going to change our pH value. So that was supposed to be the proof you need to accept. Only look at the first H in a dissociation, okay? All right, moving on to diprotic acids. She's not here today. Thank you. Okay. Diprotic salts, I mean. So this is a different kind of problem. It's still what we did yesterday. Do we recognize sodium NaH2PO4 as a salt? Right, it has a metal and a polyatomic in it. So the first thing we talk about doing is figuring out which ion actually undergoes hydrolysis. H2PO4 minus is the thing that undergoes hydrolysis. I'm going to kind of split this in half because I need to have some work to do. There's a little bit of work I got to do before I can do this pH solving. So if I were to start my rice table, I would start with H2PO4 minus. This is going to cause some issues. This is a diprotic anion. When I add water to this, like we're supposed to, what's going to happen? So you're saying the H2O is going to donate to the H3PO4? That's a possibility. But can't something else happen? Yeah, it sure can. That H2PO4 minus could donate, making H3O plus HPO4 minus 2. That's the problem. So we got to figure out which one happens. And to do that, we're going to write the two equations and actually figure out which K goes with it and all that kind of stuff, and I'll explain it to you. Yeah, this is fun stuff. So when you see a problem like this, you'll recognize it. The polyprotics are going to be all the ones in that stepwise dissociation. So it's always going to be one of those systems in a salt that's going to cause this problem. My suggestion, and you just got to go with me here, is write all the steps from the beginning of the acid down to where it can no longer donate. So you have a visual. You have to trust me on this. So we're going to go ahead. We know that this comes from what acid? H3PO4, right? So let's go ahead and do our dissociation equations for this. H plus HPO4 minus 1. That's represented by Ka1. Okay? And then we're going to do HPO4 minus, and we're going to dissociate that, and we're going to get, wait, H2 minus 1. That's the problem. Okay. Then we're going to get HPO4 minus 2, and that represents Ka2. And we've got numbers for that on your table. And then we're going to take HPO4 minus 2 and make H plus PO4 minus 3. And what represents that? Ka3. So once you have this written down, these problems become a lot easier. Okay? So what I'm going to do is write the two possible equations that I need to pick from to start my rice table. So H2PO4 minus plus H2O, what is that going to make? Give me one, whichever. Which way do you want to go first? Okay. H3PO4 plus OH minus. All right, and then we're going to leave some space because you're going to have some math to do. H2PO4 minus plus H2O makes, this time we're going to have this be the acid, and it's basically these ions we're dealing with are amphoteric. They can be acids or bases. So we're going to make HPO4 minus 2 plus H3O plus. Okay, so I just want to start with the second one first because it does match something from above. If you look at this, we're going from HPO minus 1 to HPO4 minus 2, and it's acidic. Does it match any of those up there? This is the second one. Do you see how it's just the water and the H3O plus? That's the only difference. So this is Ka2. So someone tell me the value for that from your table. 6.2 times 10 to the negative 8. Okay, that's Ka2. Now with this one we've got a bit of a problem. First off, do we need a Ka for this equation? Look at the products. What do we want? We want a Kb, right? Well, this is kind of, in terms of what it's making, the reverse of one of the things from above. I'm not going from negative to the H3PO4, but do I have one going from H3PO4 to that? That's Ka1. So I'm going to take Ka1 and convert it to Kb. How am I going to do that? Kw. So Kw is 1 times 10 to the negative 14th. What's Ka1? .5 times 10 to the negative what? All right, so let's go ahead and find that value. We need both of these values because one of them we'll have to use in our rice table when we're solving our expression. So what do we get? Okay. Thoughts? Which one do you think we use? The 1.33 times 10 to the negative 12th or the 6.2 times 10 to the negative 8th? The question is, which one is more likely to proceed in the forward direction?
6.2.
The larger one. You pick the larger K. That one's more likely to happen, so that's the one we're going to use to determine the pH. So now we just treat this like any other normal rice table. And so our products then, we've decided, are going to be HPO4 minus 2 plus H3O plus. The original concentration was at 0.1? 0.100. So y'all know how to do this. Go ahead and get started while I'm talking. Minus X plus X plus X. Now it's just a normal rice table. So we're going to, boom, trump that. And so we get Ka, or is this the Kb one? This is the Ka one. Ka is equal to H plus times HPO4 minus 2 divided by H2PO4 minus. So we get 6.2 E negative 8 is equal to X squared over 0.1. So X, which is equal to my H3O plus concentration, is what? 7 point, can I get a second on that? Yay, moles per liter. So that leads to, give me a, because of the K's, give me a 2 decimal place pH. 4.10. Ah, the last period, the last section, first period got that one. They didn't get the other one, they got that one. Ooh, my ankle just gave out. Okay? How you feeling? All right, so the next one, we're just doing the first part, at least this part, because I want to make sure you know how to pick the right K. I think this part you're pretty good at. If you know how to do this and want to work ahead and get me that answer, that would be awesome. Some of you can do that. I'm going to try to copy this. Take this to the next page because I am that lazy. Group. Copy. It's pretty swank. Good old smartboard. All right, determine the pH. I'm choosing to copy this because it's the same set of things we'll be looking at. All right, so 2 ions this can break up into. We can again make sodium plus or HPO4 minus 2. It's obvious that this is going to be the one that we're going to use, and it's clearly going to be one that is diprotic. So if you're taking the test and you're like, is this one that can go both ways? If it doesn't have multiple Ks, it can't do all of this that we're doing today, okay? So it has to be something that has multiple Ks. So if you see you're provided with a bunch of Ks and you ask for the pH, it probably is one of these. So that's kind of your hint. So what 2 equations could we potentially have? Well, we could have HPO4 minus 2 plus water. Which way do you want to go this time? What's the base? The thing is the base? Okay. H2PO4 minus plus OH minus. All right. And then the other way we can go, HPO4 minus 2 plus water. We can make PO4 minus 3 plus H3O plus. One of them is always going to match one of the Ks. Which one matches exactly? Because they're Ks, it's probably the acidic one that matches, right? So this is the acidic one. What K represents that? 1.8, woo, it's tiny, times, 4.8 times 10 to the negative 13? All right, so this is our Ka3. So that was this one. We went from HPO4 minus 2 to PO4 minus 3. All right. This one is a basic one, so we're going to need the Kw divided by, which relationship is this? Going from 2 H's to 1 H. Ka2, and that was 1.6 E negative 8? 6.2 E negative 8. So what is my Kb then? 1.6 times 10 to the negative 7. Okay, did any of you get the pH? Move ahead of me or no? Working on it? Okay. I'll set it up while you all calculate. I'm not even going to talk. Oh, which one did we pick? That would be a good question to ask. We picked this one this time because this one's larger, right? So we're going to use this equation in our rice table. Is it 0.1 again? Ooh, X is equal to OH this time, which is 1 point what? .26 times 10 to the negative 4. POH to 2 decimals. And if y'all are getting something different out there, holler at me. And then pH is 10.10, right? Everyone else get that? Okay. So that is that. So again, the hardest part here is to figure out which equation we use. That looks really fancy. It looks impressive, like y'all actually are doing some cool stuff. Okay, if you have questions on this, anybody? All right, really quick, I'm just going to comment a little bit about some structure of acids that we need to kind of talk about in terms of strength. Up until this point, you guys have kind of basically memorized some rules and just accepted some things, okay? But there's a reason that acids like HF are much weaker than acids like HI, okay? There's a reason behind that. And so when we're looking at binary acids, you're literally just looking at the tug of war that exists between the H and whatever it's attached to. What do we know about the characteristics of F? It's the most electronegative. It's tiny. It loves electrons, right? So if F is attached to an H, what is it doing to that H? It's holding on to it like crazy, right? So the stronger it holds on to it, what can you tell me about the strength of the acid? The weaker the acid is, right? Because to be an acid, it has to give away that H and dissociate. So the super electronegative F is hanging on, small percent dissociation. Something like I is like, I don't care, take it. Less electronegative, huge, nucleus is far away from the valence electrons. It more readily dissociates, making HI stronger, okay? So when you're looking at binary acids, that's what's going on in those cases. Now there's a couple acids we have to compare. Say we're looking at acids that have the same central atom, but have different number of O's. And we've had that 2 more oxygen than hydrogen rule. And this is going to kind of explain why. So if we have something like HClO, there's actually, the way these are set up, there's actually an O and then the Cl. And then comparing it to something like HClO4, go away, little guy, go away. We'll compare it to this guy. It's O, and then we've got a Cl. No, God, what is my problem today? It's Friday. Can you not tell? I can tell it's Friday. HO Cl, and this has now 3 O's. So I'm comparing the extremes just so you can kind of see. So this is kind of their structure, okay? and this is a very organic topic, like we talk about this hardcore in organic chemistry. What makes an H go away? If an H plus leaves, do we agree we're leaving behind an anion, right? It's going to be negatively charged, okay? The more stable this anion is, the more apt it is to give away the H in the first place. If it's happy as being a negative, it's going to more likely have a negative charge on it and kick off the H. OCl, yeah, we got this little electronegativity action going on. O is a little bit more electronegative than chlorine, or is it? It's really close. They're super close in electronegativity. These guys are kind of hanging out. They're pretty happy being stable as a negative ion. But this, we have got all these oxygens, electronegative, pulling, and these guys alone together are super stable as a negative, also because of the size. The larger it is, the more spread out that charge is. We call it delocalized in organic. The more delocalized that charge is, the happier this is as a negative ion. This is like a negative electron heaven compared to this. So this is more apt to want to be negative. If that's the case, this is more apt then to kick the H off. Okay? Does that make sense? So that's why the more oxygens we add, the more stable that anion becomes, the stronger the acid. Okay? If we're dealing with same number of O's, we still think about the stability as an anion by looking at the difference. There's the difference in all those acids. Which is happiest being a stable anion? ClO3 or IO3? The ClO3, because chlorine's more electronegative. Since it's more electronegative, it's going to be happier being in this state than the ion, IO3 will being as a negative. This one's not as happy as that is. So this is more apt to kick away the H, making a stronger acid. Okay? So that's just kind of the idea of how structure contributes to strength. That's a really good question. I think it'd be equivalent, honestly, because that ClO3 is a very stable anion. So I don't know. Let me think about that, and I'll get back with you. It's a good question. But we get the idea. So if you have any structure-related questions, those are the kinds of things we're looking at. So the formal lecture's done. I'm not done with y'all. I'm going to do some pre-lab questions with you guys to make your weekend a little less stressful. So we are done with this unit. Bye-bye.